Okay.
Okay. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
The
Honorable Acting Head of Department of Informatics, Dr. Eng Adibo, SSIMCOM.
The honorable guest for today, Professor Tom Heskes from Radboud University, Netherlands.
All lecturers from the Department of Informatics, Faculty of Science and Mathematics, Diponegoro University.
And all participants attending this meeting. Good afternoon and maybe good morning, Professor Tom, and welcome to the Visiting Professor Program held by the Department of Informatics, Faculty of Sciences and Mathematics, Diponegoro University. Let us introduce ourselves first. My name is Ivan Benawan, currently studying informatics in Diponegoro University.
And my name is Catherine Kania, currently studying informatics in Diponegoro University as well. It is our pleasure to be the master of ceremony for today's event. Before we start the event, let me go through briefly of the rundown for today's event.
First is the opening, which is currently we are doing.
Followed by welcoming speech from Acting Head of Department of Informatics.
The third agenda is the main event, the lecture by Professor Tom Heskes.
Followed by Q&A session.
And last but not least, the closing for today's event.
Before we start the event, let us all pray together according to our own beliefs for the smooth running of this event without any disturbance, and also for hoping that everyone here will be able to learn a lot from this rare opportunity, the lecture given by Professor Tom Heskes.
Without further ado, let us start the event, starting with the opening speech from the acting head of Department of Informatics, which will be delivered by Dr. Eng Adiwibowo, SSIMCOM. Ladies and gentlemen, please welcome Dr. Eng Adiwibowo, SSIMCOM.
To Dr. Eng Adiwibowo, SSIMCOM, the stage is yours.
Okay, thank you, Ivan and Catherine. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Yeah, first of all, let us thanks to Allah Subhanahu wa Taala, the most gracious and merciful God, because with His permission, today we can gather here to join the visiting professor, even in data science. And I hope that you all as safe and well in this pandemic situation. I pray this challenge COVID-19 will pass soon and we can return to usual activity and we can meet each other. I mean, on behalf of Department of Informatics, Faculty of Science and Mathematics, Universitas Diponegoro, I have to great pleasure to welcome you all to the visiting professor event. And this event is for the first time for the outside participant. And I'm happy to welcome you all. And most especially for the invited professor, Tom Heskes from Radboud University, Netherlands. Thank you so much for honoring our invitation and spend all your very busy time and tight schedule. And I want to use this opportunity to congratulate the organization team, Mr. Fajar and team, and other, Ms. Rismi, and also lecturers and also students. Thank you, Mr. Ivan, Mr. Catherine, for their foreign side and also very hardworking to make this event reality. And once again, I want to heartily welcome you all this event, and it's my pleasure one time to say thank you to and welcome in visiting professor event of Informatics Department Faculty of Science and Mathematics. And hopefully what we are doing today is useful for our progress in future, and thank you. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Waalaikumsalam.
Waalaikumsalam warahmatullahi wabarakatuh.
Thank you very much, Dr. Eng Adiwido SSMCom, for the welcoming speech. We are now continuing our meeting to the next agenda. That is the lecture which will be delivered by Professor Tom Heskes from Radboud University, Netherlands. The lecture will be moderated by Mr. Fajar Agung Nugroho, FCOM MJS.
Thank you very much for this nice introduction and opportunity to give this lecture. It's really great to kind of share my screen, but in particular my thoughts about AI and data science, right? So the title of my talk is really artificial intelligence or data science, and what's the first? So what I hope to do in the next hour or so is to give you a feeling of what AI is about these days. Why is it such a hot topic? Right? Yeah. So why are so many people talking about it? And also, I will spend quite some time on trying to discuss with you where we're heading, right? So where are we going with artificial intelligence and data science? Okay, so this is a bit of the outline of the talk. So I will talk about breakthroughs in artificial intelligence. I think the main breakthroughs that we see today are because of deep learning. So I will spend a bit of time trying to give you a high-level understanding of deep learning. Then I will zoom in on a bit more on what I think will be one of the next steps, which is causal discovery, or how can we find cause-effect relationships from real-world data. So I'll say a few words about that. And then I will go to the outlook. So where are we heading with the field of artificial intelligence and data science? Okay, so breakthroughs in AI. So the first question that already kind of bothers me a bit, or well, that many people are kind of thinking about, so how do we find artificial intelligence? So nowadays, at least in the Netherlands, when you talk about artificial intelligence, then a lot of people are saying that they're doing artificial intelligence, and maybe they are, but it's not so clear anymore because so many people are claiming to do AI these days. So I particularly like this definition here, which says that artificial intelligence is the science and engineering of making computers in ways that, until recently, so this is an important point here, we thought required human intelligence. So the key point here is that it seems a bit to be about engineering, about informatics, about computer science, but things that we thought we couldn't really do yet, and now we can, and now we're kind of on the same level as humans, or maybe even better. Okay. So that's a bit the idea behind the AI, and it's very well formulated in this citation. So it's not so easy to determine what's difficult and what's easy for computers. So maybe now we know quite a lot, right? So we know, for example, that chess is relatively easy to solve. But in 1966, one of the really top people in artificial intelligence, Minsky, so he saw that computer vision was kind of easy and chess was very complicated because it required a lot of reasoning and things like that, right? So easy to say in advance what the hard and the simple topics are. As we've seen in 1996 that Deep Blue, a computer from IBM, managed to beat the world champion in chess. At that time, it was Kasparov. And it was really amazing that they could do that, and they really kind of sold it as not so much as AI, but as kind of a way to make computers better. And in particular, they were very proud of their hardware, that they could really do this. But of course, there were also kind of many clever computer science tricks in there. When we look back to it, we would say that it's a lot of search, right? So a lot of number crunching that they did at that time. And the chess programs that we have these days are quite different, in particular the new ones, from the way that chess was solved back then. Here's another breakthrough, maybe not so obvious, but I think this one is actually also really impressive. It's again IBM, and IBM played another game, and they called the computer Watson, and Watson won Jeopardy Jeopardy against the two best players in the US at that point in time. And Jeopardy is the kind of game where you get the answer and you have to guess what the question was. Okay? So if I say Trump, then you probably have to say something, who's the president of the United States? So that would be kind of the right answer, because that's the question to the answer that you're given. So this is a very complicated task, because you need a lot of context information. But IBM managed to solve that. And in particular, they didn't use the internet. So well, they used the internet to get the knowledge, but then put everything onto a single machine and managed to solve this problem. So in terms of natural language processing, I think this is a major achievement. Would we still call that AI? I guess we would. So they're using very many kind of clever tricks specifically for understanding language and gathering and combining lots and lots of information. Now, this is the one that you may have seen, because it's not so long ago. So this is about playing the game of Go. And there was a team like Google DeepMind that made this program called AlphaGo that managed to beat the kind of best player, I guess, in Go at the time, and maybe still, Lee Sedol. Right? And so there's even a movie about this, which is actually a really nice watch. So if you have the opportunity to see that, I would definitely do it. It really shows that AI, if you really want to solve these kind of problems these days, is really kind of a team thing, right? So you have to work in a team. You need many people to work on this. So what they managed to do was to rephrase kind of playing games like Go as a reinforcement learning problem. And they could use deep learning. I will say a bit more about deep learning in a minute. And they could use lots of self-play. So they had basically an old version of the computer playing against a newer version of the computer, and then learned a lot from all these games that they could play. They had very clever new tricks, right? So the deep learning algorithms that they used were a bit more advanced than the ones that were used until then. And really important, they had lots and lots of computers working on this, right? So huge computing power. So very clever ideas, but also lots of hardware there. I think for us as computer science and AI researchers, we expected this to happen at some point in time, but this was like 10 years before we expected that we could be able to kind of solve this game of Go, right? Or at least beat the kind of human best player. We're not there yet, because Alpha Star, and so that's AlphaGo, and now there's Alpha Star. So it reached the Grandmaster level last year, but it's not, I think, better than kind of the best player in the world yet. So these kind of computer games, I don't play them, but probably some of you do. So these are even harder than playing the game of Go, right? So this computer program is already really, really, really good, because it's better than 99.8% of ranked players, but it's not the top of the world yet. So here's still some improvement to be made. The kind of technology that they're using there is a bit similar to the technology behind AlphaGo and then later AlphaZero, but with one additional, let's say, trick or solution, and that's called multi-agent reinforcement learning. So instead of having one kind of algorithm, you could say, doing reinforcement learning, they have multiple ones, and then depending on the strategy of the opponents, they can pick which one to actually use. So these are really, I mean, amazing achievements, right? And lots of large teams with huge computing power, very clever people working on that. Now, if I think back, and where in my own field of AI was kind of the main breakthrough, then it's probably best visualized in this way. So there is this competition called ImageNet. It runs every year, and it's about classifying images, right? So there were 1.2 million, really, so a lot of images that you can use for training a model, and then they leave aside like 100,000 images for testing. Okay, it's quite complicated because there are 1,000 different object classes. So in this image, and I hope you can see that. So let me see if I can show you that. So if you see the pointer here, so this is a leopard. So you should be able to classify this as a leopard, and probably here you can see a ship, and well, so these kind of things you have to be able to classify based on just given the image, right? Now, what people did before is that they really thought very hard about kind of clever features that you can take from these images. So for example, for leopard, you probably want to define images that relate to somehow these pickles that they have. So there's probably some feature that can tell something about pickles, or whatever. Right, so and people thought very hard about all these kind of features that they needed for solving these types of problems. And those are the blue solutions in this graph. And you can see that, well, they did quite okay, right? So in 2010, the performance was like 72% correct for the best solutions. And then every year it got a bit better, right? So maybe the year before it was 68%, and then in 2011 it was a bit better, like 75%. And then here you suddenly see a gap. So there were two teams using a completely different solution based on deep learning. So those are the green ones, right? So the green solutions are all based on deep learning. And they jumped from like 75% to like 85%. And that's a huge gap in just 1 year. What you saw the year afterwards is that almost all teams immediately jumped into deep learning, except for a few losers here. So they still tried with the old solutions, but of course they stood no chance really. I mean, it's possible to kind of reach the same level as with the current deep learning techniques. Okay, and then after that, there was only green solutions, right? So everyone is now working on deep learning, trying to improve that. And on these tasks, they achieve now like close to 99%, right? So, and this is really human performance, because as humans, we also make mistakes, right? We're not kind of perfect in classifying so many images in so many different object classes. So now, I guess, as a field, we need new challenges, right? So this is a new challenge. It's a joke, of course, but it's kind of nice, right? So you can make these kind of collections, and here you have to decide whether it's a Chihuahua, which is these very small dogs, or whether it's a muffin. And some of them are not so easy. But this is not serious. I mean, we're not really working on that. We're actually working on very more important problems, in particular in medical imaging. There's a lot of work going on medical imaging these days, where everyone is now using deep learning. So this is just an example. This is an example of and the people, well, some people of Google DeepMind together with people from several hospitals, and this is for classifying eye images, and then based on this image of the eyes to determine what type of disease it's probably going to be, and then where the physician should try and focus on, right? So you can turn it into what we call a classification problem. So you have to say it's this disease or that disease and so on, and then you can make plots of that. So this curve that you see here on the right hand side, it's called an ROC curve. Oh, I don't want to have this. Let me this. Okay, so what you can see here is it's a so-called ROC curve, and what you should have in mind is that the more you have it in the top left corner, the better it is, because then you classify almost all images and you make hardly any mistakes, right? So that's the basic idea. And then the dots in this image are particular people looking at this image, so actual humans. And you can see the performance of the system, or you can choose where to pick it, but for example, the star would be a particular performance. You can see that it's really good, and it's better than at least most of the humans. So yeah, so for these kind of tasks, we're definitely at a level of kind of human performance. So this is work from Mosen. So Mosen worked as a PhD student at our university. So this was a collaboration between my department and the department at the hospital, where they're doing kind of great research on medical imaging. So this was about white matter lesions in the brain. But to be completely honest, it doesn't really matter what kind of structure you're looking for. So you can just apply deep learning if you have enough labeled data, and then see what the system can try and make of it. So this is very relevant research with great medical application. And let me see. I have no idea why this happened, so let me quickly restart. No idea. Display settings. Something weird with my image, but I hope you cannot see it. Okay, so let me continue by telling a bit about deep learning, right? So I hopefully I've been able to show you that deep learning is kind of a really hot topic there. And it's very important to then at least understand a bit what deep learning is about, right? So that's what I will try and do in the next. I have to fix my screen. This is always complicated, right? Doing this on such a distance, but we're getting there. Okay, so this is a deep learning. So the inventors, you could say, of deep learning, or it's not so clear who the real inventors are. So they got you could say the Nobel Prize. We don't really have a Nobel Prize in computer science, but it's called the Turing Award. So it has more or less the same status for kind of the deep learning revolution, right? So and these are Joshua Bengio, Jeffrey Hinton, and Jan LeCun. There are many more people, as they also acknowledge, who worked on kind of deep learning and made this progress, but they are definitely kind of the godfathers of the deep learning revolution. So let me put this a bit into perspective, because I mean, I've been talking a bit about data science, right? I mentioned data science, and we have deep learning, you have artificial intelligence, and it's good to realize that these are kind of somewhat different topics, right? So somewhat different fields. AI already started in the 50s. I gave you a quote from Marvin Minsky, who thought that the chess was a lot harder than computer vision. Well, not really, right? So, but that was already in the 50s. And then there were many rule-based systems. Machine learning started maybe in the 80s, and a prototypical example is a spam filter, as you can see here. And then the breakthrough with deep learning was in the last more or less 10 years. The deep learning is really a subset of machine learning. So many solutions that you find these days in AI are based on machine learning, and then not deep learning, but kind of standard machine learning. And machine learning itself is, again, a subset of artificial intelligence. So data science, right? So that was also the topic of the lecture. So data science is kind of a part of that. So it overlaps with artificial intelligence. And there are also topics outside of data science that I won't be covering today. So data science for me is machine learning, deep learning, plus some other topics. And I will be focusing today mainly on machine learning and deep learning. Okay, so what are these kind of deep learning models, right? And I will specifically talk about deep learning models for classifying images. And for that, people use so-called convolutional neural networks. And you can probably understand a bit how they work, right? So when we talk about a convolution, it's kind of a filter. So maybe sometimes you're using PowerPoint and then you're trying to, or some other program where you want to kind of make the picture or the image that you have look slightly differently. For example, you want to blur it a bit, or you want to sharpen the edges, or you want to focus on a particular part of the image. Well, the models that can basically do that, so we call those filters. And so we have filters for edge detection, for sharpening, for blurring, and so on. And so what people did kind of before the deep learning hype was that they thought a lot about the kind of filters that you need for a particular problem, right? And so for some problems, you may need kind of edge detection a lot, and for other problems, you may need other filters. The point now is that with deep learning, if you just have lots and lots of images, then we don't have to specify these filters anymore. It kind of learns what these filters should be. So it tries to kind of find these filters itself, basically by learning it. So given just enough examples, it can learn these filters. And it's organized in such a way that in the first layers of a deep layered neural network, you have relatively simple filters like edge detection, maybe sharpening a bit, and things like that. And then they are combined to kind of more complicated filters. And they're combined again and again and again. So that's why we have these kind of layers. So you get a whole hierarchy of kind of features that the network learns. Okay? So that's how you can detect kind of these types of images. And maybe a nice example of that is, and this is already quite old, so it's done by people from Google Brain. So they trained a huge neural network on slices, or so on images from YouTube, right? So they just picked YouTube videos and showed all these kind of YouTube videos to a huge neural network, and they basically asked the neural network to learn the type of filters that you need to correctly represent all those videos. And indeed, what you then saw was that in this network, in the first layers, you could see these kind of filters there, right? So these edge detectors for lines in particular directions, you could see different detectors, and further in the network, you could find nodes that specifically became active when a face was presented to the network. They could also find nodes that specifically reacted when there was a cat presented to the network. Why a cat? Because there are lots and lots of YouTube featuring cats, right? So I'm not sure if that's the same in Indonesia, but there are so many YouTube videos with cats in there, much more than you have videos with dogs, actually. So they couldn't find any nodes there with dogs, but definitely with cats. Okay, so this is just an example. And now these kind of deep learning models are used in many different ways. So this is an example from a spin-off company that I'm a bit involved in, machine to learn. So they worked on a project where the goal was to automatically count cars, right? To basically monitor traffic. And you have to do that really fast. And so for these networks, they have all kinds of different architectures. So you have ImageNet, and you have AlexNet, you have whatever. And this particular network is called YOLO, not for you only live once, but for you only loop once, because it has to be really fast. And as you can see, it does a really good job on segmenting the cars, and then you can quite easily count them. Well, maybe the latest advancement are the so-called generative adversarial networks. And you may have heard about that. So people talk a lot about that in the context of fake videos, right? And fake images. So how does it work? Actually, it's not that complicated. So you have two of these kind of deep learning neural networks, one to generate images and one to try and classify images. And then the classification should be that the classifier should be able to distinguish between real world actual images and the images that are generated by this other neural network, right? So one network generating images, so you get a sample, and then you have a sample from real world images, actual images, and then you have another neural network that tries to make sure that it can discriminate between the real world images and the images that are generated by the network. And then they go into competition, because this one tries to make images that are so difficult or so close to the real world images that the discriminator cannot see the difference. And the discriminator tries to see the difference all the time, right? So they go into the discriminator has to be better again, and the generator has to be better again. And at some point, the generator starts generating images that really look like the real world images. So that's the idea of the adversarial. So the adversarial stands for this kind of competition that you have between the generator and the discriminator. So how can you use this? Well, here's an example of different images of people and then interpolating between them. And as you can see, everything in between really looks like a human, even though these people do not exist, right? So there are only 3 images: Obama, I think Jennifer Aniston, and someone else. And then everything in between really looks like people. Another way that you use that is to present such again, so such a generative adversarial network with lots and lots of paintings, right? So images from paintings, and then they ask the network to generate a new painting. And this is the formula that they use for that. So there is this min and this max, so that indicates this competition between the generator and the discriminator. And then some formula, and you can try it out at home, and then you can try and sell your newly made painting for like 400,000 US dollars, which is, I think, quite a lot for just a painting made by a computer. Okay, so this is a bit about deep learning, right? So, and why is it such a success? Well, you need lots of computing power. But the good thing is that you can quite easily parallelize them on GPUs. So people are using GPUs for that. You need huge data sets, but we have those data sets nowadays, right? Which is quite different from like 20 years ago. And that's also why you see that companies like Google and Microsoft and Amazon are really good in deep learning, because they have access to these data sets and they have lots of computing power. It's also that we have better models these days. So the basic principles for deep learning were already out there like 20, 30 years ago, but now we have tricks to really make them work, right? So the rectified linear unit is one of them. We're using dropout, batch normalization, and all kinds of other tricks that make things work these days, right? I think what really helps a lot is that now there's a lot of open source software and courses and tutorials. So if you want to, you can look on the web and you find lots and lots of information, and you can start by yourself, basically based on all the information that is out there, which I think is really good and really an improvement compared to like 20, 30 years ago, where companies were always kind of hiding the software. So now you're not sure whether Google will kind of put their kind of latest developments online, but definitely all the researchers there are very much into kind of open source software. So at some point, what they have invented will be made open source. And definitely, I mean, deep learning is state of the art in computer vision. You can also apply it in speech recognition. There are really, really cool applications in natural language processing, but we have to be a bit careful there, because there's no silver bullet, in the sense that there are many applications where deep learning will not work, right? So you need special type of data in some sense, right? So for images, it's very clear that these convolutional neural networks are very well matched to kind of the type of data, right? So there are these kind of features like edges and combination of edges in actual images. So that's why they work. So it's not because you do something kind of random to it and then it suddenly works. No, it's really well thought of what type of architectures we need. We don't have to specify the features anymore, but we do still have to specify the architectures that we're using for these kind of problems. And we know what architectures to use for computer vision, speech recognition, and natural language processing, because there's a lot of structure in that type of data. If you have data where there's no such real structure, it's much more complicated to make deep learning neural networks, or maybe even impossible, that are better than kind of good old-fashioned machine learning techniques, such as random forest or support vector machines or whatever, right? So there's a lot of structure in your data, then deep learning can really help, and you also need lots and lots of data for that. If there's no such structure in your data, then there won't be anything better than classical machine learning. Okay. Another disadvantage of deep learning in general, maybe also of most machine learning approaches, is that you're always specifying what's input and what's output, right? So you already know kind of that you want to predict what the image is, what the class of the image is, right? So there is no, well, you don't really care about causality or about what's cause and what's effect. You just want to predict or to classify. So in a sense, you're only looking for associations. And that's perfectly fine for many applications, but there are definitely also applications where we'd like to do more. We'd like to understand really what's going on, so that if we're going to do interventions, we're going to invent policies, that things get better, right? And so with typical deep learning things, we cannot really do that. So that's the field of so-called causal discovery. I will quickly go over this because otherwise I don't have enough time. But the basic point is that correlations do not tell you everything, right? And we know that. So there is a correlation between the incidence of lung cancer, which is here on the y-axis, and the consumption of tobacco, so smoking, and you can see for different countries that there's a clear correlation. It's funny because there's an even larger correlation between chocolate consumption and how many Nobel Prizes you win. So this is chocolate consumption along this axis, and this is how many Nobel Prizes you win along the other axis. The correlation is even a lot stronger than in the case of tobacco versus lung cancer. But of course, there's no direct causal relationship here between chocolate and winning Nobel Prizes. Not that when you start eating more chocolate, you have a higher chance of winning a Nobel Prize. It doesn't work like that. So we know more or less how it works because we kind of understand what's going on. And that's what we're looking for with these causal models. So here's the third example that, well, I don't have any data, but you can think about that, right? So probably if you have a data set about accidents, then you will find that in many cases, people break a lot when they are having an accident. Right? So if you just look at the data without really understanding what's going on, then you will probably realize, well, if people break a lot, then they get into an accident. So probably you shouldn't do that, right? So please don't break because otherwise you end up in an accident. It's not like that, right? So, and we understand what's going on and we can make models of that.
Professor, you are mute. I don't know how.
So
Yeah.
for how was that? I have no idea. I didn't touch anything, but anyway.
Yes, Zoom is.
So how far should I go back?
Yes, I guess.
One slide or two slides?
Yeah, just one.
Okay, just one. Okay, good. Let me do that. So I was explaining that in these kind of cases, well, there are correlations, but we are really interested in causality. So how does the world change when we intervene, when we make changes, right? And we can have models for that. And in this case, for example, there is a clear causal link between smoking and lung cancer. There is no such link between chocolate eating and Nobel Prize. There are links there, but they are what we call related to a common confounder. So if the country is very wealthy, then there's more education, maybe more research, and then at some point in time you can win the Nobel Prize. Here it's even worse in the sense that there is definitely a negative effect of breaking or crashing, right? So definitely start breaking when you think that you enter into a crash, but the reason that you're breaking is because there's danger or maybe a slippery road and so on. And so this indirect effect is very strong, which makes it you will find a negative correlation at the end, a positive correlation at the end of the day between braking and getting into a crash, even though the direct effect is negative. And that's what we try and sort out with causal discovery. So there's a lot of research on that. And I think even the kind of top people in AI, like Joshua Benjo and others, they're really looking into that now because that's probably going to be the next step for artificial intelligence, machine learning. How can we better find cause-effect relationships from actual observational data? There's a nice book by Julia Pearl, who's one of the godfathers of that. And we have actual software for that as well. So we've been working on that. So this is Elena Sokolova, who now works at Amazon. So she studied, for example, the relationships between ADHD and autism spectrum disorder. And then you have lots and lots of data on that, questionnaires, brain data, characteristics of children, of the mothers, and so on. And then you can try and learn kind of the causal relationships between these particular variables. Right? So this is just one example, and you get these kinds of models. But actually, you don't have to go to Amazon or you don't have to go to Nijmegen to learn about that, because there are people like Patrick himself who's also, so you should definitely invite him. So this is the joint paper that he wrote last year. where we try to do the same, or well, actually, Fatih try to do the same on understanding iron deficiency in the context of anemia. And he found really nice models that can really help to understand what's really going on in these types of diseases. So you should definitely invite him to present it at some point in time. Okay. So this is kind of nice, right? So we have deep learning. I already sketched a bit where some of the research is going these days, which is more to trying to find cause-effect relationships. But what's actually going on? So where is AI heading? So for deep learning, but in general, we see that we have more and more data. We have faster computations because the computers are getting faster, and we have better models. But it's really nice, and we get better machine learning AI systems. The computation we know, right? So there's Moore's law, and Moore's law tells us that our computer will be getting faster. I think twice as much in 1.5 years or something like that, right? You have to buy a new one. Your computer will get slower, but if you buy a new one, it will be a lot faster. And the question is, how long can we still have this kind of law, right? But we're still on it, it seems, although it seems to flatten off a bit. There's a lot of cloud computing, and we're gathering lots and lots of data. In fact, big data has its own Moore's law. It's doubling every 1.5 years as well. And I think the Moore's law for computers is a bit slower even. And we will have 40 zettabytes. I'll look up how many zeros there were in 2020. So it's amazing. So think about YouTube, think about Facebook, Twitter, Netflix. Lots and lots of data is being gathered on a daily basis and per second. People are putting sensors everywhere. So in the UK, someone calculated that there are 5 million surveillance cameras, so one camera for every roughly 10 people. And on a typical day, when you're just walking around, they will see you through 100 cameras. We all have cell phones. And in the industry, you see similar trends. So companies are putting sensors everywhere on their machines. So they're measuring a lot. They really don't know often what they can do with them. But then there are also concerns, right? So there are these concerns, and Elon Musk is one of the people talking about that AI is really a threat for humanity because computers are getting more and more clever, and at some point they might be so clever that they're more clever than us, and they kind of overtake us, right? So that basically the robots are more important and have more to say than the humans. And of course, we know all these science fiction movies where they play these kind of scenarios. The question is it really going to happen? And the reasoning is a bit that we have this exponential growth, right? So that computers are getting faster, we're gathering more and more data. And at some point, if the computers will have more computing power than all human brains together. Question is, will it happen? So the first question is, so how long does it take that we can make computers really that are as clever as we are in basically all tasks that we can do, right? So we call that artificial general intelligence. So I will discuss that a bit more. And the other question that you can ask is, well, if the computers are so clever, will that then also lead to a hostile takeover, right? Or can we somehow prevent that? Okay, so this is to ease you a bit. So this is a video from Robocup. So Robocup is a competition between robots playing soccer. So this is from the final from 4 years ago, but it's So as you can probably see, they're not really good. We're not really good at robot soccer yet, right? And there are two complications there. So one is the robot itself, right? And the other thing is how to work together. So it's kind of a multi-agent learning problem, you could say, which is very complicated to solve in terms of strategy and how you should play this game, right? So there were these two difficulties. When you think about robots, Boston Dynamics comes to mind, which is, I think, the company which is the furthest in developing humanoid robots. And I would say this is really amazing last year, actually. So this is what a robot can do these days. But this is not a cheap one, of course. But this is it's really cool. They also have these robot dogs that you may have seen. This is cool, right? Okay, so let me see. Yeah, so we have these competitions, right, in the field of AI. So I talked about ImageNet competition, but there are more. And this is one where you have to answer questions. So you get an image and you get a question in natural language, right? So for example, for this image, the question is, what's the mustache made of? And first, it's relatively easy. We immediately see that the right answer is bananas. But it's not so clear for an AI system. So on these kind of competitions, AI systems maybe have 50%, 60% correct, but not better than that. And we as humans are a lot better. So here, definitely, we're not close to general AI yet because it's such a hard problem. And this is another example where AI systems failed very seriously, I would say. So this is Microsoft Play. So there was a chat robot, you could say, so a chatbot who was put out on Twitter by Microsoft a couple of years ago, and it could speak natural language. So it could basically say anything it would like to say. And it was very easy for people on the internet to steer it in a particular direction. And within, I think, well, less than 24 hours, it was talking completely racist language. Right? So it was obviously not intended, it was not put in, but it just went off in this particular direction, steered by humans. So we have to be very careful. And after this, no one ever tried to put something like this open on the internet. So chatbots with just free language, no one uses them. So it's always kind of restricted to a particular set of answers and then pick kind of the right answer, maybe out of 200 or maybe 10,000 different answers, but always restricted. No free language because we don't know how to really control that. Another issue, which is often in the news, I guess, is related to fairness, right? So, and fairness is not so difficult to understand why that's an issue, because if we think about machine learning, we're learning models out of data, and then we're going to use those models to make decisions, right? That's what we do. And then people realize that when we use these algorithms, and sometimes even called Franken algorithms, that can be a serious risk. And the risk is because if the data is biased, then the model will be biased, and then the decisions will be biased. And there are many examples of that. And it can be even worse because if the decisions then end up again in the data, then it will be kind of a positive feedback loop, which makes things even worse. So one of the people who noticed this was Latanya Sweeney. So she noticed that when she typed in her name in Google, then she got ads which were related to lawyers trying to keep her out of prison. She said, why would I get these types of ads? And then when she entered another name like O'Brien, which is a typical kind of white male, then she didn't get those. Right? So that's really strange. So it so appeared that dark people got different ads than white blind people. A bit similar if you do a search on, well, if you did, because now the system is a lot better. If you did a search on CEOs, so bosses of kind of big companies, then you only got pictures of white men. You got no females there, which is, and even not in the percentage, right? So the frequency of white males before you would get a female as CEO to reality. And that's really, I mean, a bad thing. And it's partly because of the data, but of course also because of the algorithms that we're using. Now, we as humans, of course, also have our biases, right? So this is a picture from psychology, and these are all the kind of different biases that we have. So there are lots of them. And so we shouldn't really blame just the algorithms for doing for making biased decisions. We also do that ourselves often. So we're now getting into the direction where we feel that if you want to have less biased decisions, we maybe should even use algorithms. We can try and use algorithms to make less biased models from biased data. So there's a whole field now working on fairness in machine learning. And here you can see the number of papers in this particular field, right? So it's really exploding there. And that works on trying to think about methods to make sure that you get unbiased models, or at least less biased models, even though there's a lot of bias in the data. Because then your decisions will also be less biased and you can try and solve them. So there are many different ways to define fairness. There's a really nice book that came out last year called The Ethical Algorithm. It's a very nice read, so I can recommend that. And this is Cynthia at work giving a keynote at some top conference on individual fairness in this case. So many different definitions of fairness. Maybe not as a surprise, the one that I like relates to causality again. So for me, fairness is really about asking questions that are related to what if, right? So what if this person was not a male but was a female, or the other way around? And what if this person was not white but in fact black, or was not black but in fact white? Would he or she have been arrested then as well? Okay, so we call that counterfactual reasoning, and it's really into the area of causal analysis. So that's why also some people feel that we have to go more and more into this causal direction with machine learning. The other concern that people have, quick look at the time. So the other concern that people have is that the models are getting so complicated, or these deep learning models are so extremely complicated that we don't understand them anymore, right? So we have no clue what's kind of inside these black boxes. But there are definitely many algorithms out there that try to kind of visualize what's going on into these deep neural networks. And I already gave you this example of Google Brain with the YouTube video. So this is in a sense similar. So you can try and understand what these kind of nodes in these networks are really looking at. Okay? So what they are focusing on. And there are quite a lot of different algorithms for that. So we're getting there. We're making things better and better. And also here, we have to think about humans, right? And so there was a nice discussion on Twitter. So in Europe, we now have a particular law, the GDPR, it says that any algorithm that we're using has to be able to explain the output that it generates. Right? And then you would say, well, then deep learning is kind of illegal because we cannot really explain what's going on there. But on the other hand, if we humans make decisions, it's also not so easy to explain why we make these decisions. I mean, also we're not explaining them in the sense that we're pointing at neurons in our head, saying, okay, this neuron at that point fired, and that's why the other neuron that fired, and then they all together came to the conclusion that blah blah blah. It's not the type of explaining that we do, right? So we have to be careful not to ask more from the algorithms than we do from based on the decisions that we make ourselves. So that's a nice discussion that is currently ongoing. But in the meantime, we're trying to improve kind of algorithms that can really explain why machine learning models make particular decisions and why they go for particular classifiers. So this is called Lime, this one on the left-hand side. And I put it here because of the very nice title of the paper. Why should I trust you? Explaining the predictions of any classifier. So this was really popular, but it's now completely superseded by something called the Shep values that kind of incorporate Lime as a special case and are more elegant and easier to kind of understand and work with. And so I'm pretty proud. So we have a recent paper in the kind of main conference in the field called NeurIPS on causal Shapley values, where we try to incorporate kind of causal relationships between the features that we're using as input to these neural networks or random forest or other machine learning models, and then try to kind of give an explanation of the output of the prediction models, right? That relates back to these causal relationships, or that incorporates these causal relationships between the features. So if you're interested, we're going to have a nice paper on that in a couple of months. Okay, so this is a bit about kind of what the hot topics are in machine learning and how are we trying to make them more responsible, right? So responsible AI is a very important topic these days. So let me see if I can now spend the last maybe 10, 15 minutes on explaining where we are and where we're probably heading. And so the next video that I'm going to show is what we would really like to have in terms of self. It's more of a friend, but I kind of really like the video, so let's have a look. Now you probably understand that this video is fake. It's a very nice. It's very nicely done, but it's not an actual situation in real life. Although I have to admit that when I was in Indonesia a couple of years ago, it sometimes looked a bit like this. But in Western Europe, it's completely different, maybe. Although in the big cities like Paris and London, it's maybe also a bit like this. But anyway, so but this is not what we have right now. So we don't have self-driving cars that are so good that we can have this kind of behavior. And even worse, I mean, this was from Uber 2 years ago. So there was this really bad accident because, well, self-driving car, the driver wasn't really paying any attention, and the self-driving car didn't pick up that there was actually someone walking on with their bike on the street. And so if you think about self-driving cars, I don't know if you've noticed that, but the investments of companies is not increasing a lot these days. It's probably even decreasing a bit, right? So we're not really getting there. It's not getting a lot better. And so self-driving cars seems to be where we are currently in terms of being able to have a functioning AI system in the real world in a more or less open world. So if you think about these games, right? So the breakthroughs that I mentioned seem to be related to games, but games is a very closed world. We know what's going to happen, right? Play the game of Go, very difficult, but it's a closed world. So you know what you can get, basically, at the end of the day. If you have self-driving cars in an uncontrolled environment, so not somewhere out there on a campus where there's hardly anybody there and so on, but in kind of real world where people do all kind of weird stuff, then it's much harder. And we do not seem to be actually where we would like to be, and where we may have expected to be there maybe five years ago. I think people expected that there would be self-driving cars by now, but there aren't any. At least not kind of fully functioning in just open traffic. So, and for me, the issue is really, right, so we have training data, we make a model, we make decisions, and then it should work on test data, which might be quite different from the training data that we have. And there might also be this feedback loop again from test data, so things that you see in the real world, and then maybe you make the wrong decision, or maybe not quite good, and then you need to kind of be able to update your model while it's driving around, right? And it's not so easy. So it's a very complicated, difficult problem. And these feedback loops we don't seem to have fully under control yet. Okay, so let me now ask you a question. So we're going to do a little Kahoot, and let's see how this works. This is always kind of the tricky part of a lecture like this, right? So maybe it's going to fail completely. But the question that I want to ask to you is whether we're going to have artificial general intelligence and how long it's going to take, right? So, so let me clarify this distinction there, right? So we have artificial narrow intelligence. We definitely have that. Computers are better than us in playing chess, even in playing the game of Go. So in many tasks, they are better than we are, right? So no doubt, we already have artificial narrow intelligence. The interesting question is, when will we have artificial general intelligence? So that there are no tasks that a computer can do, that cannot do better than we as humans can do that. Question is how long it's going to take. So let me see if I can start this Kahoot. I already prepared it a bit, so I'm going to stop sharing for a minute and go to the Kahoot, and then you hopefully also see the pin. Hope you know how it works. Yeah, I'm going to put it here. I'm going to need my Zoom here. Where's my Zoom? Here's my Zoom. Okay, I'm still there. I'm going to start a Kahoot. Okay. So let me share my screen. There we go. So you know how this works, I hope. Maybe you have the app. If not, then you can go to www.kahoot.it and then use this game pin 6296208. And the question is going to be, how long is it going to take until we have artificial general AI? There will be 4 options. The first option is going to be within 10 years. Then, I have to do this top of my head, probably between 10 and 30, 30 and 50, well, maybe 30 and 100, more than 100, or maybe even never. So, but you'll see the options that you can take in a minute. So now the question is whether you really paid attention there, right? More and more people getting there.
We just got some info from our department that the winner will get a prize. So please participate and do your best.
Okay, we already have 62. Wow. Good to see so many people among us. It's good because I can also have a bit of a break, which is also nice. And you as well, maybe. Wow. Okay. Still people joining. This is going to be a great quiz, actually, because I get lots of statistics here, which is really nice.
If all are going to join, so we expecting to have 253.
Okay. Well, we're going down now, so maybe I should start. Okay, so let's start the Kahoot. So the Kahoot is about artificial general intelligence. 3, 2, 1. How long does it gonna take until we have artificial general intelligence? And you have 4 options, less than 10 years, between 10 and 30 years, between 30 and 100 years, more than 100 years. If you say never, choose more than 100 years. So pick your answers. So you can choose between kind of the red one, the blue one. You probably know how it works, right? So you still have 5 seconds. You don't, I mean, you cannot calculate this one. So you have to give your opinion there. Okay, there we are. Nice, nice. So this is the result of the jury, right? So some people say less than 10 years. Most of the people say between 10 and 30 years. Quite some people also say between 30 and 100 years, and also some of you think more than 100 years. So I don't know, right? So did this question, right? The question has been asked for a long, long time. Let me go back to my slides here. And now share the right screen. I want to have this one. Yeah, there we are. Hopefully, yeah. Okay, so this question has been asked for a long, long time, and both to experts and to non-experts. The question has been asked for like 60 years, and over these 60 years, every point in time, the distribution was more or less what you also have, right? So here you see your distribution. So the maximum is somewhere in between 10 and 30 years. So that's what most people think. Some people think a bit faster, some people think a bit longer, and some people maybe think not that. So think that already had happened, right? Then the distribution is also like that. So we also 60 years ago, we thought that artificial general AI would be there within more or less 30 years. Or maybe 20 years, right? So somewhere between 10 and 30 years. But it didn't happen. We're definitely not there yet. So that's why if we extrapolate this type of behavior, it's probably never going to happen, right? If you think about that. So it's very difficult to predict when it's going to happen. But we also have to be very careful that we're not kind of in the hype of the moment, right? So many points in time in the past, we also had this feeling, oh, it's going to happen pretty soon, but it didn't. Because it's a very complicated problem, and also because I guess as humans we're still pretty clever, which is maybe a good thing. Okay, so if we can, right? So if we can make these computers more and more clever, then they might have many advantages over us as intelligent being. It's much easier to copy a computer than to copy a human being. There are no emotions, which can be an advantage, which can also be a disadvantage. I don't know. And in some cases, it could be an advantage. And well, there are many more of these advantages that you can probably come up with. The important question is, can we build friendly AI? And at this point in time, we don't really know how to do that. There are definitely people thinking about that. But for now, it's for sure that we have to keep the human in the loop. So in terms of self-driving cars, it's nice that we're kind of trying to get there, but make sure that the human is still in control, right? And that's also what I think we're doing, right? So cars are getting more and more clever and more automated, but we're don't giving full control out yet, and we shouldn't, right? So we have to keep the human in the loop. And if we think about what the real issues are with artificial intelligence right now, then the narrow AI is of much more concern than kind of this big picture of robots becoming that clever that they're going to take over us and the rest of the world, right? That's not going to happen very likely very soon, but we can make systems that can do a lot of harm to a lot of people using AI already now. Right? So we can easily make drones with kind of automated image recognition and then doing all kinds of nasty stuff that we don't want them to do, right? So, and that's much more concerning now than these robots that might take over the world in maybe 20 years, maybe 30 years, probably never. Okay, so I won't read them up, but these are my take-home messages. We're gonna probably share the slides. So these are personal, right? So you don't have to agree with them. But for me, AI is like any other technology, so there's not so much special about it as some people would say probably. And every technology has its pros and its cons, and we have to be very careful about that. Maybe another one is it's the third one, and I already pointed it out a bit, right? So lots of the progress that we've seen in the last 10 days has been fueled by deep learning, but it's still statistics, right? It's still number crunching. And the example is with these YouTube videos, right? So we can see nodes that specialize on cats because there's lots of cats in YouTube videos, but we're very bad at representing kind of things that we hardly see. So the exceptions, we as humans know what to do if there's something exceptional, like in the self-driving car with the incident, right? We know what to do, but a computer, it's very hard to tell them kind of what's happening out there in these very weird cases. So we're very good at gathering the statistics, right? So the things that happen a lot, but to get to the next level of intelligence, we need more than that. So causality is definitely one thing there, but there's going to be more. And when it will happen, no one knows, right? So we have to be careful not to say it's never going to happen because we simply don't know. The point that I'm trying to make here is that we need another paradigm, and that's what it makes it so difficult to predict what's going to happen. It's not extrapolation of what has been happening in the future, right? So we need something else. So deep learning is not good enough. We need something else on top of that to make the systems more and more careful, okay? And that's also what we have to keep in mind. We don't have to be worried so much about these robots taking over the world, but we have to concentrate on all these byproducts of current technology. And it's not just what I mentioned, right? So not just kind of a military maybe use of AI, but also ethical aspects that I discussed a bit, legal aspects, unemployment, inequality, those kind of things. It's much more important to work on those than this kind of media savvy stuff about robot domination. Okay, so that's basically what I wanted to discuss this morning with you. I hope you enjoyed the presentation and at least got something out of it. And then I think we have time, Mr. Fajar, for questions and hopefully also.
Yes, we already have a few questions here. The first one is it possible to use machine learning in the area of astronomy? If yes, how is it going to work or help? Yes, like that.
Yeah, actually, machine learning is already used a lot in astronomy, but mainly for image recognition, right? So astronomers, well, they cannot go out there and kind of make pictures, so they have to do it mainly from the Earth or from the other side of the moon, or maybe, yeah. So there are lots and lots of pictures, basically images, and then we can apply deep learning on those images to classify them. And that's been done a lot, actually, for supernovae, for all kinds of different structures of stars, for finding black holes, all kinds of different problems are basically tackled with applying deep learning on images in astronomy. Yeah.
And we also have a raised hand here, Risang Baskoro.
All right. Good morning, Professor.
Good morning.
I would like to ask a question. I don't know if it's out of topic. Let me introduce myself first. My name is Risang. I'm a student in informatics, in computer science in Diponegoro University. I would like to ask a question regarding to AI and its jobs. With AI, it's really good at helping human with their task and doing their jobs, such as in medical, transportation, and industrial, or even astronomical sector. Will AI take humans' job and replace human in the future, or will it create some kind of new jobs, and how will it affect humans' daily behavior? Thank you.
It's a very good question. Yeah, so there have been different reports on that, right? And some people claim that, well, many jobs will be taken over by AI systems. I don't think that's what's going to happen. I think parts of people's jobs will be taken over by AI systems. And those tend to be the less interesting parts. So I don't think we have to worry about that. But with change of technology, right, we've seen it in the past. I mean, there have been changes in technology, and then new jobs arise, and old jobs will disappear. We also see this in the COVID-19 case, right? So some jobs will appear, some people can make maybe even money out of it, and some jobs will disappear. And that's the same for AI. And so we have to be flexible there. But the reports that say that kind of 90% of our jobs are going to be gone, no, it's not going to happen like that. It's going to be maybe 10%, so that would be my guess. But also for this 10%, yeah, so we definitely have to carefully think about that. But I wouldn't consider this to be fully due to AI. It's more related to computer science in general and to automation, right? We're automating more and more tasks, and AI kind of helps in there. But there are also very simple types of automation that are more relevant than AI itself. Yeah.
Okay. Other question is, how we determine that the result is having overfitting, like that, Professor? Or is it by calculating the errors? If yes, then how?
Okay. Yeah. So I didn't really talk about these technical details in this presentation, right? About overfitting. I did say a bit about that 2 days ago in my other presentation. Overfitting definitely is an issue, but I think we have really good tools to prevent overfitting and to check that the model is not overfitting. And the main tool is using cross-validation, so leaving data aside that we don't use for optimizing the models, and then checking that the performance on the set that we have not used for fitting the models is as good or not terribly worse than the one that we have on the training data. So we have ways of preventing overfitting. I think overfitting is more of an issue in the sense that the data that we might see in the real world does not correspond to the data that we have collected to train our models. So I think that's a more serious issue than overfitting itself. So overfitting we have under control. The point that if we have a self-driving car, we already gathered lots and lots of information and gathered lots and lots of circumstances, but there are still some out there that the model has never seen. I think that's a real issue because we cannot really grasp the whole distribution of things that can happen. So for that, we also have methods, right? So that's called domain adaptation, maybe a bit of transfer learning. But those are still kind of difficult problems that we have to get better in.
Okay, the next question is, in which cases should we use deep learning, conventional machine learning, or AI? In which cases they are performed best, I guess?
Yeah, that's a good question as well. Yeah, so for me, AI is kind of the whole field of both rule-based systems, machine learning, and deep learning. And so AI systems in the old-fashioned sense of rule-based systems are very good still if you don't have a lot of data that you can learn from, right? So and you have to ask experts to really tell you, okay, so how should we work in this case? So to give an example, we would love to have lots and lots of data on COVID-19 patients and how they should be treated. But right now we still have to ask experts, right? So we're asking experts to kind of tell us what they would do and then put that into systems and then hopefully put the systems out there, get more information and update the model using machine learning. So rule-based systems are still very important there when you don't have a lot of data, but you can make use of expert knowledge. Machine learning versus deep learning. So deep learning has been very successful on image recognition, speech, and language. It's not yet successful on many of the other more tabular data sets, right? With, for example, characteristics of patients with age and gender, and then maybe some brain data, and maybe some genetics data, and so on, right? So deep learning in some cases, if you have lots and lots of data, it might be kind of slightly better than random forest or anything else, but then you really need lots and lots and lots of data, and to really work hard to tune the deep learning system. So I haven't seen any convincing evidence yet that in those kind of cases where the data is not as structured as for images, speech, language, deep learning really outperforms kind of good old-fashioned machine learning in terms of random forest or vector machine. Okay, so it's really so deep learning systems are good if the data is really such that there is kind of this hierarchy of features in there, right? Which you have in speech, which you have in language, which you have in images, because then it makes sense to kind of have simple feature detectors in the early layers, more complicated ones in the later layers. And for that type of data, deep learning is great. For other type of data, the benefit of having all these layers is simply not there.
Okay, I was expecting for causal related question, but it's not here.
Right, you. Yeah.
It's
I
new for
basically
us
left it
here.
for you to discuss.
Okay. And the next question is, I remember a guy trying to make an AI to beat Tetris. Do you know Tetris, the game of blocks?
No, I
The,
don't.
oh,
Well, let me check.
it's like a falling blocks in different shapes. The AI keeps failing over and over again, so that the AI decided to just pause the game because the AI cannot lose if it doesn't play. This is unpredicted. So how to solve this unexpected condition? Is it just stop the AI for pausing the game, stopping its ability to pause?
Yeah, that's a good one. Yeah, so when you think about how to optimize your AI system, you have to think very carefully about the optimization problem that you pose it, right? And there might be side effects that you didn't think of. So another example of that is when you think about, okay, you ask an AI system to solve the world food problems, right? So to make sure that there is enough food for all the people on the earth, and you phrase it in that way, then the AI system might think, well, maybe we need less humans, then we also need less food, right? So you have to be very careful in how you define your optimization problem to not allow the AI to find a solution that you really don't want to have. So there are some constraints in there that you forgot to specify and that the AI had to take into account, but you forgot to mention. So that's why we need this human in the loop control still, because well, for some problems that are so important to us, we don't know whether we gave it the right optimization problem. So we have to be very careful there. And a similar problem, right? So if the AI system says, well, then I'm not going to play, then we should put in the constraint that it has to play, because otherwise, yeah, it's not going to learn anything.
Okay. I guess this is going to be the last question. Normally, we have machine learning to have data that's already there, right? Like downloaded data. And the question is it possible to update the model of a machine learning from stream data, that data that is live produced? Is it possible?
Yeah, definitely. So there are machine learning systems working on streaming data, and that's of course perfectly fine. So it doesn't, in that sense, matter a lot, as long as the streaming data that you get has similar statistics as the data that you've seen before and that you've learned from, right? So if it's going to be completely different from anything you've seen before, then the machine learning system will fail completely on that particular type of data, and it can kind of relearn based on that. That'll be fine. But then if the next set of kind of streaming data is again completely different, then it doesn't know, right? So it's always learning from experience, and the new data that you want to predict on, or that you somehow present, should be statistically similar to the data that you've seen before, because otherwise, yeah, basically lost. You don't know how to do that. I think the challenges are, right, which is a bit going into that direction. It's again in the area of transfer learning and domain adaptation. So domain adaptation is the problem where you've learned on one set of data, and then there are some characteristics that you can transfer to another data set that you haven't seen before. But still, the data that you haven't seen before is still quite different, right? And you can do this with kind of pre-trained models, or well, there are many different tricks for that. So that's, I think, where we're making progress. So domain adaptation, in the sense that we've learned a machine learning system on one domain, and now we're going to use it in another domain, and we need much less examples than to already have a really good start. So that's the kind of applications that I see these days, and that you could think of as kind of streaming data from some other set of data. Yeah.
Okay, thank you, Professor. Can we have one more question?
Sure.
What should we do to keep the privacy of the data when implementing AI?
Yeah, that's also a good question. I didn't touch upon that, right? So, but privacy is another of these topics within responsible AI. And so I covered fairness and explainability. Privacy is another one, and I could talk. Well, not me personally, but people could talk on that for hours. It's also very important. So there was also this book, The Ethical Algorithm, that I showed on the slides that I recommend. It also has a part on privacy. So there are two solutions. Roughly speaking, there are probably more. So one is an area called privacy preserving data mining or machine learning, where you somehow change the data such that the statistics stays more or less the same, so you can still learn from it. Right, so you can still use your models and learn these models, but you don't have to give the system access to the real data. Okay, so that's kind of one solution. So you're basically perturbing the data such that you cannot trace back what the original data was. So there's one solution, which is a bit related to kind of more the machine learning algorithms itself. The other solution would be, and that's also a pretty hot topic, is that you bring kind of the learning systems to the data instead of the data to the learning systems. So that's also sometimes called distributed learning. And so what you then try to do is then, the machine learning systems can only ask questions basically to the data set, and also only get the statistics back, right? So never individual data points. And that related to somewhat the hardware solutions, so that you can really do that. So that's another area of research which is pretty prominent these days. So distributed learning systems would be a really good solution, but not all machine learning algorithms still work properly in that particular setting.
Okay, thank you, Professor. I guess we come to the end of our lecture and discussion here. And so I will return this session to our host, Miss Catherine and Ivan.
Okay, thank you very much for Professor Tom Heskes for the amazing lecture.
And thank you to Mr. Fajar Agung Nugroho as ComNCS for moderating the lecture.
Before we continue, we will have a virtual photo session together.
To all guests and participants, we would like to ask you to turn on the camera.
Okay. For all guests and participants, maybe for documentation purposes, feel free to open the camera.
And who will take the
Okay.
clicking?
In my screen, there are several videos that are not on yet, so
It's okay.
maybe from Catherine.
Yes, mine is okay.
Okay. Okay, maybe we start from the first page, okay? From Risang to Nugroho. 1, 2, 3, cheese. Okay. Okay, for the second page, maybe we can turn to the second page from Rahadian Fajar. Maybe Catherine, you can lead.
Okay. 1, 2, 3, cheese.
Okay. To the third page, maybe. Are there videos? Ah, okay.
Oh,
This
we
is the
have
last page, okay.
9 pages.
Oh, but not all the participants turn on their camera, maybe. So until the third page. Okay.
Okay.
Catherine, you may lead.
Okay, thank you for the participation. The photo session is now finished.
Okay.
Again.
We wish you all a great day. Wassalamualaikum warahmatullahi wabarakatuh.
Thank you,
See you
Professor
guys. Thank you
Tom.
very much. Thank you very much,
Thank you,
Professor.
Prof. Tom.
Thanks a lot. Bye-bye.
Bye
Have a
bye.
good day.
Bye.
Thank you again.
Have a good day, sir.
Okay. Oh, Papa sudah ya. The winner.